Hi there, my name's Aaron Lanchman. I'm a professor of electrical and computer engineering at Georgia Tech. In today's lecture, what I would like to do is to use the initial value and final value theorems to do some reasoning about our canonical second-order filter structures, but in the time domain instead of the frequency domain, and without having to actually invert any Laplace transforms. So we had our canonical low-pass, bandpass, and high-pass functions, all of which had the same denominator. We like to normalize the low-pass form by putting an omega n squared in the numerator. We had a 2 zeta omega n s in the numerator of the bandpass form. And the high-pass form, we just had an s squared and didn't need any normalization constants. And these normalizations here let this low-pass form have a gain of unity at dc. The high-pass form naturally has a gain of 1 at a theoretically infinite frequency, and this particular form of the bandpass filter has a gain of 1 at the natural frequency. So what I'm interested in knowing is that assuming that we input a step function, so I'm going to let my input x of t be a step function ut, what are the resulting step responses? But for the purposes of this lecture, I'm not going to try to compute what the step response is for all time. I'm just going to ask what the step response looks like at 0. And then I'm also going to ask what each of these step responses looks like at infinity. And what I really mean by the infinity here that I'm putting in quotes is I'm asking what is the limit of the step response as t goes to infinity. So the initial value and final value theorems both involve taking limits of the Laplace transform as the Laplace transform variable itself goes to a certain limit. But what you're taking the limit to in the Laplace transform domain is opposite of what you're taking in the time domain. And another thing that it's important for me not to forget, that I often do forget, is that you're not actually taking the limit of the Laplace transform. You're taking a limit of the Laplace transform times the variable s. Now, the reason it winds up easy to forget that s a lot is that you're often using the initial and final value theorems, or particularly the final value theorem, I should say, to look at step responses. So if you think about that, well, there's a 1 over s arising from our step response input that always winds up canceling with the s that's out in front. Again, the sort of cancellation that you get here is such a common pattern that it's very easy to forget that there is an s sitting out in front, but you need to remember it's there in those cases when you're not using these theorems to look at step responses. All right, if we let s go to infinity in the low-pass function, I have some constant over something squared that's going to infinity, so that's clearly going to be going to 0. In the case of the bandpass function, as we're letting s go to infinity, we're going to wind up with an s over s squared kind of form in the limit. As s goes to infinity, you wind up with some sort of s over s squared kind of form, which is really like a 1 over s kind of form, which in the limit as s goes to infinity is going to give us 0. But in the high-pass form, well, as s goes to infinity, we wind up with a form like s squared over s squared in the limit. The s squared term here is going to start to swamp the s term and the constant term here for large s. You have something like s squared over s squared as s goes to infinity, so that's going to give us 1. All right, the final value theorem is even easier to reason about because there we just let s go to 0. So if we let s go to 0 in this expression, we'll wind up with omega n squared over omega n squared because these two terms drop out, and that will leave us with 1, omega n squared over omega n squared. When we zero out these terms here, I'm left with 0 over some constant, so that's going to give me 0. And similarly, when we zero out these terms, I'm left with 0 over a constant. So that is also 0. So this at least gives us a super rough feel of the overall start to end shape of the function, going from 0 to 1, 0 back to 0, and then 1 to 0 for the low pass, band pass, and high pass cases respectively. And importantly, we're able to get there without having to do any partial fraction expansions. Now, these initial and final value theorems are very useful for sanity checks on the cases where you do slog through all that work and compute partial fraction expansions and inverse Laplace transforms. If the results you get from these theorems doesn't match your Laplace transform, you may want to think about that a bit more. Before we finish here, I must once again warn you that these theorems only hold if the respective limits in the time domain actually exist. If they don't, it's perfectly possible to take some Laplace transform, multiply it by s, take some limit, etc., and get some number. But if the limit doesn't actually exist, then that number is meaningless.